Kia ora koutou, I'm John Hosking, I'm the Dean of Science here at the University of Auckland, and it's my very great pleasure to welcome you both to the University and also to the inaugural lecture of Professor Geoffrey Waterhouse, the first science inaugural lecture of the year. And I begin with an apology for the late shifting of venue. We've had intermittent power issues in Building 303. We thought it was just a little bit too ironic to have a lecture involving alternative energy storage being canned by a lack of power. So warm welcome to Jeff's family, who's sitting in the front row. Glad to have you here. Geoff works at the cutting edge of green chemistry with a focus on addressing key science challenges behind several of the UN Sustainable Development Goals, such as decarbonisation of society, pollution abatement and human health. Much of his work focuses on developing nanocatalysts for a wide range of chemical transformations, most of which support decarbonisation of the global energy sector. A major result of his research has been the discovery of low-cost catalysts for water splitting and oxygen reduction evolution reactions, which are key processes in water electrolyzers, fuel cells and metal air batteries. He also works in the area of low-cost optical, photoelectrochemical and electrochemical sensors for environmental monitoring and the detection of threats in foods. Geoff has been amply recognised for his work, including receiving a University of Auckland Research Excellence Medal, the New Zealand Association of Scientists Shortland Medal, the Royal Society Te Aparangi McDiarmid Medal and a James Cook Fellowship, as well as consistently being rated by Clarivat as a highly cited researcher. He is also a distinguished professor at Henan University. Geoff is an Auckland graduate, one of our own, undertaking bachelor's, master's and PhD here. Probably appropriate, he's in the clock tower then for this lecture. Before joining the staff, initially as a research fellow, then later as a senior lecturer and associate professor, before his most recent promotion to professor, which we're celebrating tonight. Tonight, Geoff is going to talk to us about nanospace, the final frontier, as it says up there. In doing so, he will attempt to answer the age-old question of does size matter? His motto perhaps could be from small things, big things grow. Geoff, the floor is yours.
Kia ora koutou, welcome everyone. Thank you, John, for that introduction. It was a very good bio. I think I'll use that myself later on in life.
Stolen, yours, mate.
Oh yeah, no, very good. Yeah, obviously looking around the audience here, it's a trip down memory lane. I can see people I studied with here as a student at Auckland University, people I was taught by, people I have since taught, people I've met in other walks of life at later stages of my professional career. Some of you I haven't seen before and may have just been here for the catering. That's fine, I used to do that myself when I was a student. But obviously it's an honour to have my parents here. So my lovely wife Dong Shao, our daughter Jane, her fiance Matthew, and of course my parents, Joan and Geoff Senior, aged 84 and 85 respectively. About 52 years ago they started to do these sort of gene engineering experiments, and eventually those experiments have produced a University of Auckland professor. So yeah, well done Mum and Dad. So in preparing this lecture, like all people delivering an inaugural lecture need to do, you need to say, what is an inaugural lecture? It's quite different to a normal presentation you'd give at a conference, so I had to look at a number of universities' descriptions of what an inaugural lecture is to try and get a sense of what I was supposed to present here today. The first one reads a bit like I'm under examination, so I didn't really like that. But if you read down and go through these things, you find out that actually it's more about reminiscing on your experiences that have led you to this point, thanking a lot of people, because no one gets to professor at a university without a lot of people supporting them on the way, and there are many people in this audience who have helped me on my journey, so you have my great appreciation. You're also supposed to try and entertain and inspire, and that's what I want to do. I don't just limit it to inspiring young people. Old people can be inspired as well. University of Auckland, you know, we don't discriminate based on age, so let's try and inspire young and old. So John's talked a bit about my bio. Obviously, I'm very proud of where I've got to at this stage of my professional career, but really this tells nothing about the journey to get here. So I've had some luck, some fortune along the way, a lot of ups and downs. So it's that up and down journey I want to share with you today, because I think it's more interesting than just reading about where I am at this point in my life. So 1972, great year in music for those of you who are familiar with it, but I got my first promotion, getting out of that sort of embryonic fluid, getting out in the world, seeing what's happening, where I could have impact. Then I did my primary schooling at Sylvia Park School in Mount Wellington, followed by high schooling at Penrose High School. Interestingly, we'd come into the university for our 7th form or year 13 exams. A lot of mine were held in medium chemistry, where I subsequently, you know, did a lot of lecturing in later life, so that was quite interesting. I then did a BSc majoring in chemistry, taught by a lot of people in the room tonight. I was in Brent Kopp's first lecture at the university here. You might say that, you know, the positive confidence he got from that experience has enabled him to go on and become one of our finest teachers here at the university. I subsequently did MScs and PhDs here at the University of Auckland. Towards the end of my PhD, I dabbled a bit with food science, being hired as a research fellow to help develop some of their new labs for undergraduate programs. Then doing a postdoctoral fellowship in the area of nanocatalysis, some of which I'm going to talk to you tonight about. Sort of came back to the University of Auckland late 2007, flirted around on fixed-term contracts for about 5 or 6 years, before finally getting tenure at the ripe old age of 40. By the time people in our school, our faculty are already becoming professors, so that was an experience. Sorry. Just there. Yeah, I'm sliding. Okay. And then obviously delighted with this recent promotion to professor. So definitely an interesting career with more ups and downs than a pogo stick. Some of you might know what a pogo stick is. It's a device you jump up and down on like this. Let's talk about the younger years, because a lot of my inspirations for becoming a scientist came from my younger years. So the photo on the left, that shows Dad, me, I think it's probably under the age of 1 at that time, with my older brother David. We'll talk a bit about him later. Obviously Mum here, me again. I don't think this was our tent from memory, this brown one with the green lid. I don't know about these old cars here. It's making me feel old seeing the design of those. But obviously I developed an interest in water, and this has continued on with my current research at the University of Auckland, where we're trying to make fuels from water, in particular hydrogen. So if you're doing experiments, you've got to make sure you're not introducing contaminants into your experiments. And this was a step I learned early on, that don't pee in the paddling pool. That affects all the experiments you want to do with water. Interestingly, in the background there, you see a garage. Okay, about 5 years later, that garage burnt down. Dad had left a can of kerosene open. My brother David, who you saw earlier, was playing around in there. Somehow a spark got into the kerosene can. Mum, Dad and I were driving down our road going, oh, there's a fire in our street. And it turns out it was our garage that was burning down. So that was an interesting experience, and that taught me another thing, that kerosene and air and a spark equals trouble if you're not balancing the composition and burn rate. So that's another valuable science lesson I learned at a young age. And of course, a lot of what I do about nanotechnology, scale is important. So this was me at a young age, where I had to communicate to Mum as how big the fish was that got away when Dad was fishing. And obviously leadership roles. This is really important in becoming professors. So here's me leading the design of some massive build. Obviously, you can't be outside all the time. I mean, I like to be outside as a kid, often would come back in summer at like 9 p.m. at night, just when it got dark. So on rainy days, we used to watch a lot of science fiction. Mum is a big science fiction buff, so Doctor Who, Battlestar Galactica, these were all TV series at the time. I like the original Star Trek episode, and there's one particular episode, normally with Star Trek, you're thinking about people with phasers, people with communicators, people with teleportation from the surface of a planet up to the Enterprise. In this episode, all that technology was taken away, and Kirk had to battle this reptilian creature called a Gorn with his bare hands. Slow moving, but much stronger than he was. But it turns out this rocky planet had a lot of minerals on its surface. And so here you can see him collecting sulfur, potassium nitrate, carbon, combining these to make gunpowder, stuffing it into a bit of bamboo. And the projectiles are used with these large rock diamonds. As a result, he was able to decapitate or injure, anyway, this Gorn. In the end, he spared it, he didn't kill it. I'm not sure that angle would have actually led to the projectiles hitting the Gorn, but anyway, this inspired me to do more chemistry. Of course, then you need a bit of schooling if you want to develop your habit or your interests. So these are my primary school days. This is my first year at primary school. Most of the years I was at primary school, I was wearing jerseys knitted by my mum, very stylish. Obviously, the tab collar's gone out of fashion, but very interesting nonetheless. And of course, another promotion, going from junior 1 year to junior 2, very important in my early development. Of course, you have to be media savvy if you're an academic, and I had a lot of exposure to this when I was young. Obviously, teacher retires, it's a big deal in the local rag. I think this was the Eastern Courier. And of course, I enjoyed outdoors, so I was part of Cubs, and you go on these camps. This was going to Motahi Island for a week or so. Yeah, great times. And of course, you get badges for achieving different things when you're a Cub. Forgot to put them in my promotion application. Might have helped, I'm not sure. But also the toys you're given when you're young. You know, looking back now, this was 1978 when I was 6 years old. I collected this toy range called Micronauts. Look at the names of the toy: Neon Orbiter, Thorium Orbiter, Rhodium Orbiter, all elements of the periodic table. You know, so there's this subtle influence. There's even a bit of French here on the box. I don't know what it's about. But of course, then things start to get a bit more seriously. 2 Christmases later, these were the books I was given. The MacDonald Encyclopedia of Rocks and Minerals. This aligned perfectly with our interest in rock hounding, travelling to places, collecting rocks from different places, trying to identify what they were. Obviously, this piece of obsidian I found on one of our holidays to the Coromandel with this nice conchoidal fracture, perfectly matched what was in the book, so we were gone. This is another book which I think all families should have, The Birds of New Zealand. I'm a big fan of sort of birds and watching them, and we'll talk about that a bit more later. Okay, but some science questions emerged from my youth. I mean, you've probably all had the same questions, and I'm here to answer those questions. So, why do leaves change colour in autumn? We used to climb trees a lot, and you'd find nests. Why are doves' eggs white? Why are blackbirds' eggs blue with these brown speckles? What are those gold spots on a monarch butterfly chrysalis? Real gold? This is what people told me because they didn't know any better. And then you realise not all colour's the same. Some objects change colour with viewing angle, like a power shell or a housefly. They got this shiny iridescence on there. So what are the origins of these things? These were mysteries I had from quite a young age. So then you hit high school and you're hoping that you'll start to learn how you can explain things. So this was the front cover of our 1988 yearbook, looking up at One Tree Hill when there was still a tree at the summit. You see some barbed wire on the fence. That was from our swimming pool. It was designed to keep people out rather than students in. The school underwent a name change in 2008. This was after the tree had been cut down. The name change was from Penrose High School to One Tree Hill College. So the current name's a bit of a misnomer. So that's an interesting fact. Another interesting fact. This school is a breeding ground for School of Chemical Sciences professors. So I wasn't the first, there's another. Bob, are you here? Bob? Oh, sorry, I didn't recognise you with that beard. It's incognito. Yeah, so obviously Bob's achieved this milestone before I did, and he's a good friend of mine, so he won't mind that little laugh. And of course, I have great memories of my time at that school. It's not one of the great academic schools, not one of the biggest, but we had a really good cohort of students go through the school at the same time I did, and excellent teachers, really committed teachers. Some of them had done master's degrees in physics and chemistry at this university. They knew what they were doing. So I did well academically and really excelled in sports. So that's something that's interesting. At that time, there was a television program called It's Academic. I'm sure some of you will be familiar with the UK program, University Challenge, where different universities go and they answer quiz questions and then they try and get the maximum number of points. So this was a school thing with students up to their 5th form year, where you go compete against other schools. Our school had bombed for 5 years in a row, and this is all televised, so, really low scores, the students just getting ridiculed when they came back to school. So the year we went on, actually, we won the first round, and interestingly, we took down the might of Epsom Girls Grammar. Why does this make me happy? My mum went to that school. But subsequently, so did our daughter Jane. And we live right next to that school now, so it's a very interesting association. And of course, I did well in sports, athletics, cricket, football, and I was the senior sports boy of the year in my 6th form year, so something I'm proud of. My sister Maria, she won it in her 6th and 7th form years and was also head girl, so she's got bragging rights over me as far as I'm concerned. So we finally get to the 7th form year, which is now year 13. I took 3 sciences and 2 maths. I got an A bursary. Again, you think about the cohort. The previous year, there'd been 3 A bursaries across the 7th form year. The year I went through, I think we had an 11. So that was a really important milestone for the school. And I also played representative cricket in the same year, playing in the national tournament at Wellington. So this was a conundrum for me. Academia or professional sport. So I arrived at the university in 1991, enrolled in a BSc, still struggling with this, tertiary studies, or spend the New Zealand winter playing cricket in the UK, trying to get into maybe first class cricket. So I decided, okay, I'll give tertiary studies a go. Did 2 chem, 2 math, 2 physics, botany and bio. I got my best mark in biology in 7th form, so I thought I'd probably become a biologist. Memories of this time, university was quite different. Full year courses, not semesters like with summer school like we have now. Fees were about $2,000 a year. The previous year they'd been $200. This was when we'd gone from a sort of free education towards paying a little bit. And then obviously most of the people who taught you had handwritten lecture notes. Nothing was printed. There was no Cecil or Canvas. If you lost your lecture notes, you're pretty much trying to get them off a friend. Long lab hours, so people did 36 hours of labs per course and you did those in half of the semester. It's very appropriate we're here today. At the end of the year, all final grades were posted by name and grade in the cloisters right outside this lecture theatre. So usually your friends knew how you had done even before you did, because we were living in Mount Wellington, you have to travel in. They were posted in the cloisters about a month before you got the final grades by post. Really interesting times. Now, this is where my career switched from biology to chemistry. Obviously, I'm interested in cricket. Cricket practices were always in the afternoons when the physics, botany and biology lectures were. Maths and chemistry were in the morning, so I attended all those classes. Net result, GPA 3.8, obvious professor material, okay? For those of you who don't know the university's GPA system, that sits between a C+ and a B- in that sort of grade range. But the fact that my friends had a whole year to ridicule me about this actually made me improve across the next 2 years. So having a bit of cajoling from your friends is sometimes a positive influence. Here's our cohort from this year, really good bunch of friends. We'd socialise a lot and all this sort of thing. I'm in the back row. Joe Gammon, Paul Harris, who's working in School of Biological Sciences, working with Margaret Brimble, obviously. Peter Rutledge, many of you will remember him. He was the son of Stu Rutledge, who was an associate professor in organic chemistry here. Peter's now a professor of chemistry at Sydney University. He always had an opinion to offer, even if you didn't ask for it. In this particular photo, he's asking me, should he be in the front and centre, the centre of the photo, because that would make a better photo. Obviously, I'm happy to oblige, but at the same time thought he might be better off on the row down. So I'm giving him a nudge in the back there. And there are other victories to celebrate, such as securing the last 3 beers at the graduation function. So fun times. But one of the good things to come out of this was from my BSc, and what I think anyone who's doing a BSc majoring in chemistry should know from their time at the University of Auckland, is these light matter interactions. So know how atoms come together to form molecules via bonds, what type of bonds can exist in molecules, and how you can use different types of electromagnetic radiation to interrogate those molecules to learn things about their structure. So for example, you can use microwaves to make molecules rotate. This is how you heat up water in a microwave. You can use infrared and visible light to basically cause vibrations in molecules, and from that you can get information about the types of functional groups or how the ensembles of atoms exist in molecules. You can use visible and ultraviolet light to excite electrons from bonding orbitals into anti-bonding orbitals, and this is what gives a lot of molecules their colour that I was interested in from my youth. You can also use X-rays to determine if materials are crystalline or not, or amorphous. So there's a lot of information and knowledge you can get from studying how electromagnetic radiation or waves of different wavelength or frequency interact with materials. And obviously, when you have light interacting with an object, it can be absorbed. Some wavelengths from white light are taken out of that light. Some of it can pass through the sample to the other side. Some of it's bounced off the sample. Other light is scattered in different directions. Some of it's refracted. So these are all interactions that you need to know, and of course know the relationship between energy, frequency, and wavelength of these different forms of electromagnetic radiation. The critical part is this visible spectrum. Okay? It's a range of wavelengths which can be seen by the human eye, extends from about 380 nanometers up to 750 nanometers. So all those things I was interested in my youth all related to the visible spectrum and how light, or visible light, interacted with objects. So if we look at these leaves, obviously a leaf growing on a tree is green. As it starts to get towards autumn, it starts to change colour, going from eventually to yellow, and then some leaves go finally to red. And that's all to do with these different types of pigments that are present in these molecules. Okay, these pigments absorb at particular wavelengths, and it's these absorptions which actually give colour. So if we look at chlorophylls down here, which are a special class of compound called porphyrins, I'm going to talk a lot about them. You see they have this ring structure. Sometimes they have a metal in the middle, sometimes they don't. Chlorophyll, the green pigment in plants, does. And you see there's a lot of conjugation, so double bonds, single bonds, double bonds, single bonds, double bonds, single bonds. That conjugation is important because that lowers the energy separation between the bonding and anti-bonding orbitals, enabling colour at visible wavelengths. If you just have one of these double bonds, this absorbs in the UV, we can't see that. So all of these molecules which give rise to colour all have that characteristic. So what happens is, when the leaf's on the tree, you have all of these pigments contained within the leaves. The chlorophyll, there's a lot of it when it's growing on the tree, and it's absorbing in the red part of the spectrum, it's absorbing in the blue part of the spectrum. We're seeing all the wavelengths which aren't being absorbed, so we see a lot of the green. When you go to these other pigments, they're absorbing at different parts of the absorption spectrum. So anthocyanins, they were what was in your red wine that you were drinking before you came in here. They absorb about 546 nanometers, which is in the green part of the spectrum. We see the wavelengths which aren't being absorbed, in this case red. So by understanding the structures of molecules and their interactions with light, you can explain their colour. And a lot of what we do in chemistry is this spectroscopy, where we're using instruments to basically probe where things absorb. But this gets interesting because eggshells also have similar compounds to chlorophyll, protoporphyrin 9, biliverdin. So a dove egg, it doesn't have any of these pigments. The blue speckles that are on there, the blue colour is coming from this compound biliverdin. The brown speckles are coming from this compound protoporphyrin. Okay. Now, very interestingly, you see these compounds are very closely related. There's an enzyme in the body which basically converts this to this by oxidizing that bond right there. Okay. Also, if you take those two hydrogens off and you put an ion in the middle, you get heme. Heme is what transports oxygen around in your red blood cells. Another observation. If you hydrogenate this bond, you get this compound. This is what makes your poop brown. Okay, in case you're wondering why is your poop brown, a combination of this compound plus bile gives the brown coloration. So very interesting. So hemoglobin to protoporphyrin to biliverdin to poop compound. Fascinating. So these were all things that I thought about in my childhood, and through my BSc I was able to answer. We've since gone on and done a lot of experiments where we've used a technique called Raman spectroscopy. We're shining a visible light laser in and trying to quantify biliverdin and protoporphyrin that are present in eggshells. Very interestingly, we did this experiment. We were able to get a piece of eggshell from the upland moa, which was the last New Zealand moa species to go extinct. And using Raman spectroscopy, we were able to show it had these same characteristic peaks here as compounds or eggshells which we know contain biliverdin. So we were able to show that these moa eggs were actually blue because they contained the biliverdin pigment. Other people have since gone back and looked at fossils. Okay, how stable are these compounds? How long can they last for? You're going to be shocked. Okay, this is a 46-year-old, 46 million year old mosquito. Okay, they've actually gone through and actually found heme pigment actually inside the mosquito from where it had bitten a mammal and had its last meal. So that's how stable these heme compounds are that we just talked about that are in eggshells. Okay, here's some dinosaur eggs. Now, Matt, I know you love dinosaur eggs. Okay, these have been shown to contain protoporphyrin 9 and also biliverdin. So this is important because the type of compounds, catalysts we're now developing for a lot of these reactions that perform similar functions to heme are based on this porphyrin structure, like protoporphyrin 9. So very interesting, and this demonstrates how stable these compounds are. Of course, colour comes from other mechanisms. I talked about this colour that changes with angle or iridescence. If we look at PowerShell, what you find is if you do a scanning electron microscopy image on the cross-section of the shell, you find these calcium carbonate tiles. Okay, they're about 400 nanometers thick. If you look at peacock feathers, the green part, you find these melanin rods about 140 nanometers in diameter. If you look at the gemstone opal, which shows striking iridescence or colour change with angle, you find these 200 nanometer sized silica colloids. So all of these materials, silica, calcium carbonate, they're normally colourless. Yet here, by engineering their structure so they have a sub-micron sized or periodicity similar to visible light, we actually can achieve colour. And it's called structural colour. So it's not the actual material itself that's giving rise to the colour, it's how that material is structured that's responsible for it. And of course we can go through all of these things that we see in our garden. Here's a steely blue ladybird. If you actually look at the cuticle of this with an electron microscope, you find it's got these chitin sheets. Chitin is a polymer of N-acetylglucosamine. Okay, that's its structure. Okay. And the fact that it has these uniformly spaced sheets means it reflects light or diffracts light at a particular wavelength, 492 nanometers, which is in the blue region. Those golden spots on the monarch butterfly chrysalis, okay, I've always wondered what they were. It's still chitin, but instead of having a uniform thickness of the chitin sheets, there's actually a change in the periodicity as you go deeper into the material. This is called a chirp multilayer. And instead of reflecting at a single wavelength like this to a maximum, it actually reflects over a whole range of wavelengths. And this is also seen in this beetle from Costa Rica called Christina origans. So this black line here, this shows the reflectance spectrum of metallic gold. You can see it's absorbing strongly below 500 nanometers. All the blue and violet wavelengths are basically being absorbed. there's electronic transitions which occur there, but it's reflecting all wavelengths above 500 nanometers. So reflecting green, orange, yellow, orange, and red. The average of all those is a sort of yellowy orange colour. What's interesting with this particular beetle is that these chitin sheets actually contain these chitin crystals which have an anti-helical pitch as you go up through the material. What happens is when white light comes in, certain wavelengths are bounced back out, but the light that's bounced back out is also circularly polarised. So you've all been to a cinema and watched a 3D movie. You put on the glasses, the left lens enables left circularly polarised light to go through, the right lens, right circularly polarised light. If we look at the beetle using the left lens, it looks the same because the beetle's reflected left circularly polarised light, but the other lens, the light can't pass through, the right circularly polarised lens. So it's showing remarkable features of nature that I appreciated when I was young, but only recently have I been able to explain. And this is another beetle moth found in New Zealand called a golden plusia. On its wing it has these scales. You think it might be the same mechanism, it's not. There's actually some chevron or zigzag pattern of chitin which is also giving a gold coloration. So a lot of my research is about just looking at simple things and trying to understand them. You're all familiar with what happens if you put oil on water. You can get iridescence from that, especially if you have a bitumen road, black, it's been raining, and there's a bit of oil floating on top. You'll see some really nice rainbow patterns. If you look at pigeon feathers, you've got these black melanosomes. So they're normally black coloured, but what's giving the colour here is actually this layer of keratin. Keratin's what your fingernails are made from, and this surrounds the melanosomes in the feather barbules. Basically, by changing the thickness of the keratin sheath, we can actually change what wavelengths are reflected, and we can actually model the colour of this. So up near the head of the pigeon, that keratin sheath is about 500 nanometers thick. We can go through, put the numbers into this equation, and this tells us we should get reflection maxima in the red, green, and violet. This is the experimental result confirming that. If we go to further down near the shoulder, it's a thinner keratin sheath. We get a different reflected colour. It's reflecting blue and red. You both know from your childhood days what happens if you mix paints that are red and blue. You get purple. And that's why the pigeon feathers have that colour. Mark, great to see you. Mark, Todd and I went to primary school, secondary school, university together. We played squash every morning as undergraduates. Fantastic to have you here. And of course, recent research has found that T-Rex velociraptors actually probably had feathers, coloured feathers. So very interesting. Most dinosaur species were still scaly, but actually, yeah, this T-Rex was probably feathered, so very interesting. And of course, we can go through and make photonic crystals quite easily by synthesising colloids of about 200 nanometers in diameter, crystallising these, and you can see that they behave just like the gemstone opal. And there's a whole lot of things we can do. We can take materials like TiO2, which is this pigment responsible for the white paint on the walls, and then actually engineer this to have colour. So this is TiO2, or this material here. Just by changing the structure in this inverse opal material, changing this macropore diameter, we can actually produce a rainbow of colour. So structural colour rather than pigment-based. And these materials have fascinating properties. If you wet them with liquids, you can actually change the colour they reflect. So here's the same TiO2 inverse opal in the air, filled with ethanol, dichloromethane, or benzene. So these solvents all have increasing refractive index, and you can see how changing the solvent refractive index is changing the reflected colour. Of course, nature does this better than anyone. So this is the panther chameleon. Okay, normally they're living in the trees, they like to be green, but if they see a female or they see a male that they want to shake off, they change their colour as a result. And they do that by, in their skin, there's a layer of dermal iridophores, so made of guanine crystals. So guanine has a very high refractive index, so it's very good for this application. And so when they go from green to yellow, they just change the spacing of these guanine crystals, and as a result, they change their colour. Sorry. We've got a video here. I'll show what the panther chameleon does. It's been sped up 8 times compared to how quickly it would do this change. So this is the original colour here. And over a period of about 3 minutes, it changes its colour to yellow. So this dynamic iridescence is really interesting. We tried to reproduce that. We embedded silica colloids in a stretchable polymer. So in this case, when you stretch the polymer, the colloids will move closer together, and this is the result. This is the type of stuff my research students do here at the university. It's really fascinating. So we've been able to kind of replicate what a chameleon skin does. Of course, that was the BSc. Now I started to think a bit further. Of course, I was still interested in playing cricket at this time. Obviously, had some success for the university club in the final year of my PhD, actually. But actually, my cricket days created another mystery. And you guys have probably thought about it the same way. When you mow the grass, that aroma, what is it? Okay, it's actually this compound called 3-hexenal down here. Okay, but there's a whole lot of other compounds, methanol and aldehydes, which are present when you inhale the vapours that come once you cut grass. And this really influenced my PhD topic, these alcohols, aldehydes. And so I did a PhD actually on industrial formaldehyde manufacture. So formaldehyde is one of the world's most important industrial chemicals, top 25 chemical. It's used to make the resins that go into particle boards and a range of other chemicals and cosmetic products. Process involves passing methanol here, mixing it with air, heating it up, adding some steam, passing it through a bed of silver catalyst here, collecting the products, and then collecting the formaldehyde product here. The problem with this process is you can make formaldehyde several ways, but you can also get a lot of other products, carbon dioxide, formic acid, carbon monoxide. The formic acid is particularly bad if you're trying to make synthetic resins. So producing formaldehyde with a minimum amount of formic acid is a real challenge. And obviously, we need to understand what the catalyst is doing here. So normally, if you're trying to convert methanol to formaldehyde, there'll be a big energy barrier you need to go over in order to get to your product. Okay, a catalyst provides a lower energy pathway to enable you to do that. And that's what the silver catalyst is doing in this particular reaction. Here's what the actual reactor looks like. It's about 3 meters wide. It's about 1 inch thick of this granular silver catalyst. And it's actually hot. Okay, you're running at 650 to 700 degrees C. Okay. This is what the plant looks like. So I worked with Hexion New Zealand. It was ICI New Zealand at that time in Mount Maunganui. Not a bad place to go every month or so to spend a bit of time. But this is what the factory looks like. Imagine something the size of a rugby field. Okay, pretty massive. PhD project. Reproduce this in the lab. Take something that's this big industrial process and then actually reproduce that on something about the size of this table here. Basically, it requires retraining as a chemical engineer and then screen catalysts from different suppliers to see which gives the best performance. So for those of you involved in research currently, if you want to do research and get a big sum of money, you apply to an organisation called the Ministry of Business, Innovation and Employment for an Endeavour program which is worth about $10 million. Usually you'd have like 5 or 10 people involved in it. That's the amount of effort required to actually get this project done, kind of why my PhD took 8 years, in case anyone's wondering. But basically from industry, they had gone through and they had screened catalysts from different suppliers. And what you see is that some of these catalysts are granular with boundaries in between the grains. These turn out to be good for making formaldehyde without formic acid. Catalyst B, which has mirror-like facet surfaces, this turned out to be crap. So understanding why a good catalyst worked well was the real challenge of this. So here's the prototype I ended up building that simulated the industrial reactor. It took about 5 years to optimize. The end results down here is that in the reactor you're passing methanol, water and oxygen through the bed of silver catalyst, and you're looking to see how much formaldehyde are you getting out. That's ultimately what's driving this. So this is the industrial process. This is what we got as percentage yields. It's pretty decent, and I think out of all the research I've ever done, I've had more publicity with the recent stuff. Nothing compares to that in terms of a personal achievement. That's my feeling about it. So obviously you can study how temperature affects things like the conversion of methanol and the formation of the formaldehyde yield. But your catalyst is also changing during reaction. It starts off looking like that. Through reaction, you start seeing all these pinholes appearing. So this indicates that during the process, oxygen is somehow in the bulk of your silver, reacting with hydrogen, then blowing out as steam, creating a lot of debris. You can see little pieces of debris around here. And this is something people forget about, that your catalyst is in a dynamic state of change. It's not just a fix. So using in situ Raman spectroscopy at reaction temperatures, we were able to show that the selectivity of the catalyst to formaldehyde or the other products was actually controlled by the types of oxygen species present on the surface. And these have become highly cited works in the field of catalysis. So obviously got out of the PhD in 2004, 8 or 9 year journey. You're kind of happy for that to end. I still had that question, academia or cricket. You might recognise Jim Metzen here. He's got a moustache. He had a moustache for the most of the time I knew him. So I applied for a New Zealand Science and Technology postdoctoral fellowship, and they were offering 25 fellowships that year. My application ranked 26th. Okay, if I hadn't got that funding at that time, I wouldn't be here right now. Fortunately, one person declined, and that meant I was given the 25th fellowship that year. So yeah, I look back on that as a pivotal moment. And that's led to my current work in nanotechnology, because that's what I started doing during my fellowship. So we need to talk a little bit about scale. Obviously, you all know 1 metre. That's 10 to the 9 nanometres. Okay, you know a millimetre. Okay, that's 10 to the 6 or 1 million nanometres. Okay, I was talking about those photonics crystals in visible light. So they're operating in that region between 100 and 1,000 nanometres. When we're talking about nanomaterials, we're talking about materials with dimensions less than 100 nanometres. Some of the materials I'm working on now were less than 1 nanometre. This is tiny. Okay, but nanotechnology is all around us, and it's been around us for a long time. I've already talked about bulk gold, how it absorbs light below 500 nanometres, but reflects all those longer wavelengths like green, yellow, orange, and red. So we see it as that sort of pale yellow colour, lustrous. Okay, but if we shrink gold down to small dimensions, its colours and properties change. So like a 5 nanometre spherical gold nanoparticle in solution will look red. So it's absorbing about 520, 530 nanometres. That's in the green part of the spectrum, and we're seeing the wavelengths which aren't being absorbed. And also the colour that's reflected or absorbed actually depends on the shape of the nanoparticles. What's interesting is gold nanoparticles, colloidal gold, has actually been used in stained glass windows for hundreds of years. So the red colour you can see there, all of that's coming from gold nanoparticles actually embedded in the glass. And of course, properties change when you shrink down even smaller. A feature of these small clusters, which may contain about 50 gold atoms, is that they show fluorescence. Fluorescence is a process because they're more like molecules than they are a bulk metal. So in molecules, if we have bonding and anti-bonding orbitals, you can excite electrons from low-level orbitals into high-level orbitals. They shake off a bit of energy and then emit light at longer wavelengths. This is typical for these porphyrin compounds I was talking about earlier. But we can go through and make these very small gold clusters, okay, and then study their fluorescence properties. So if we make them just 1.7 nanometres in size, this one absorbs at 560 and emits red light. So if you shine visible light at 560 nanometres on it, if you look at it, it'll look red. This other one, slightly smaller, if you excite it at under UV wavelengths at 320 nanometres, it will fluoresce in the blue. Okay, it's an interesting feature. We connected this to a peptide sequence here, and this peptide sequence targets cell nuclei. So we can put these small gold nanoclusters inside cell nuclei, shine light at those wavelengths where they absorb light, and then look at their fluorescence. So those red and blue patches you can see there are where we've put these gold nanoclusters inside nuclei. Once you shrink gold down to small dimensions, it can also drive catalytic reactions. So there's an enzyme called horseradish peroxidase. Okay, so peroxides in the body, these aren't good for you. They can cause damage to free radicals, or they can cause damage to biological tissues, lipids, not good for your health. So enzymes such as horseradish peroxidase are important. And these gold nanoclusters have properties similar to that. They can drive the same chemical reactions and destroy peroxides. We can also use these for detecting mercury. So here's an example where we had carbon quantum dots. These don't interact with mercury but fluoresce in the blue. And gold nanoclusters, which absorb UV light and fluoresce in the red. But gold interacts with mercury ions. So what we can do is we can have these two types of quantum dot in our system, shine UV light on it. If mercury is present, then the fluorescence of the gold is selectively suppressed. As a result, we can see a visual colour change as we increase the concentration of mercury. So we've got a way of detecting heavy metals in water based on the fluorescence of materials. The rest of my talk is going to be about our current work. Obviously, global warming is becoming a big issue. I was born in 1972, so was Mark. I think May and June, respectively. In our lifetimes, the population of humans on the planet has doubled. Okay, in my parents' lifetime, it's tripled. Since their parents was born, it's quadrupled. Okay, crazy numbers. The current population growth rate's about 228,000 extra people every day. Or the population of New Zealand in 20 days is pumped somewhere on the planet. Crazy stuff. And in the Asia-Pacific region where we live, most of our energy is currently coming from fossil fuels. Not good. We all know what this means. CO2 is going into the atmosphere, causing global warming. And temperatures aren't changing uniformly over the planet. The Arctic, much hotter than other regions. So it's predicted by as early as 2030 that the Arctic may be ice-free in summer, where there'll only be a little bit of ice clinging to the top of Greenland. Kind of scary. This was a painting done in 1899, where a group of artists was asked, what will the world look like in the year 2000? What will people be doing in the year 2000? You know, quite a long time ago now. This is it. People are living underwater, fishing for seagulls. This could be us if global warming's not combated. So how can we reduce global warming? Okay, those familiar with the MCU universe, Thanos went around, collected these infinity stones, forged a gauntlet, clicked his fingers, straight away, half of the people everywhere gone. Earth, other planets, gone. Not a bad option. Actually, as someone who's interested in pretty stones, I kind of wonder what these infinity stones are made from, and if I could make them, I wonder if I could have got to Professor earlier. Professor, just by clicking my fingers. Okay, but another alternative, another way we might get there is through embracing renewables, and this is really where a lot of my current research is at. So we're looking at ways we can use renewable energy, wind farms, solar. We can store that electricity short-term in batteries, but we need much higher energy density batteries than what we're currently making. Or we can feed that electricity into an electrolyser, split water into hydrogen and oxygen, then use that hydrogen as a fuel, using a fuel cell to convert the hydrogen back to electricity. For New Zealand, how can we reduce our emissions? I think the easiest way is through the transportation sector. Where about 19% of our emissions are currently coming from the transport, so cars burning octane and diesel. So therefore, if we look at the transportation sector, what are our options? We've got battery electric vehicles or fuel cell vehicles powered by hydrogen. So there's some people in the audience doing some great work around electric vehicles. Greg and Catherine Trounson. Greg, where are you? You're great. So Greg's driven the length of the country, showing that our current electric vehicle recharging infrastructure can enable that. Really fantastic stuff. For heavier vehicles, obviously, range becomes an issue, and that's where hydrogen, because of the fast refueling, is expected to play a more important role. So Greg and Catherine doing a great job. Great to have you here tonight, Greg. Another alternative is this form of transport. I mean, obviously, with grass, we already have the refueling infrastructure required to sustain it. But obviously, Greg, with his electric vehicle, is interested in acceleration from standstill. I think this won't appeal to you, Greg. One of the problems with moving to a green hydrogen economy, the key technologies that we need to use, we talked about it, rechargeable batteries, those electrolyzers which make hydrogen, the fuel cells which convert hydrogen back into electricity. Currently, they all use heavy metals. So those metals there, particularly platinum and iridium, they're really good for driving a lot of these reactions needed. So how can we replace these precious metals with low-cost alternatives? In particular, that first row of transition metal elements there. How can we make catalysts from those which do the same function as these precious metals? Okay, in medieval times, people were talking about the philosopher's stone. This was a magic material. It might have been a stone, might have been a powder. People don't really know, a tincture. But this had the property of being able to convert ordinary metals, base metals, into precious metals like gold and silver. Okay. When I was an undergraduate, the lab kind of looked like that. But in a modern day environment, obviously a lot of health and safety violations going on there. But I think actually nanotechnology is the philosopher's stone. It enables us to take materials which are common and do fancy things with them. So with Greg's support, we're developing this new type of rechargeable battery called a zinc air battery. Why are we interested in it? This is your normal lithium-ion battery in terms of its energy density, about 265 watt-hours per kg. These metal air batteries we're trying to develop, this is their sort of specific energy density. So you can see it's about 4 times higher. A zinc air battery has 4 times as much energy density as a lithium ion, which is currently used in electric vehicles and portable electronic devices. So how does the zinc air battery work? Pretty simple. During the discharge of the battery, when you're using the electricity, zinc's dissolving from that plate, going into the alkaline electrolyte. Oxygen's going from air into this. So these are like air-breathing batteries. They're sucking in oxygen. And this is part of the thing. Electrons are going via the circuit in this direction, and that's where you can have your device that'll be powered by this battery. During the recharge, then what happens is the zinc plates again onto that metal plate there, and actually oxygen comes out of the battery. So what we need to do is develop catalysts for the oxygen reduction reaction, which is what heme in your blood actually does when it's transporting oxygen around your body. It's actually reducing oxygen and then on the ion site and carrying that around. And obviously we need a catalyst which can do both to make this a rechargeable battery. And we're taking inspiration from EAM. So traditionally with nanocatalysis, people have been using nanoparticles. These aren't very good because only the surface atoms of these materials actually participates in the catalysis. Okay? It wastes a lot of the metal. We're interested in downsizing, actually making a nitrogen-doped carbon support with isolated metal atoms sitting on that surface. So every one of those isolated metal atoms here can actually participate in a catalytic reaction. So great energy efficiency and atom utilization efficiency. So obviously we want to have a metal. We know iron, which is in hemoglobin, can drive the oxygen reduction reaction. And so we're making these metal single atom catalysts to mimic what hemoglobin and some other enzymes do. We can do computational screening to show what will be the best metals if we coordinate them by nitrogen or coordinate them by 3 nitrogens and a phosphorus. But what we find is that if we have this simple arrangement I was talking about, like heme, where you have 4 nitrogen atoms coordinated to the metal, then the best catalyst for the oxygen reduction reaction turns out to be iron. The best catalyst for the oxygen evolution reaction turns out to be cobalt. First row transition metals, potentially offering a replacement to platinum and iridium. we can go through and make them and do some advanced characterization. And then we can test their performance in a battery. And what you find is that these metal single atom catalysts, if you apply them in a battery and look at the energy density of the battery that you make using these catalysts, it's actually much better than using a catalyst which was 28% platinum on carbon. So platinum nanoparticles, poor utilisation of platinum. Using these single atom catalysts which are modelled on heme is actually the best way to go. So this demonstrated we could make a primary battery which just gives out electricity, and in this next work we demonstrated that by the addition of some other component we could actually produce a fully rechargeable zinc air battery with performance far outperforming a catalyst based on the precious metal alternatives. Obviously this is our plan over the next few years. Our current lab batteries look like that. Even though we've got great catalysts, they're very Frankenstein-like with a lot of bolts and nuts. We really want to move through this commercialization phase, make things the size of an A4 sheet, stack these together into modular systems, or make one of the advantages of these zinc air batteries is they enable us to make flexible batteries which we can use in wearable electronics. In its serendipitous discovery, we found that if we have nickel coordinated by 2 oxygens and 2 nitrogens instead of 4 nitrogens, we can electrochemically produce hydrogen peroxide. So hydrogen peroxide is an important chemical. It's used for sterilization and other purposes. During COVID-19, production of hydrogen peroxide increased 3 times. Everyone's trying to sterilize surfaces. So we're showing that using metal single atom catalyst and by varying the coordination around the metal atom, we can actually get the product we want, in this case hydrogen peroxide. Of course, sustainable aviation fuels is a big one. Are we going to be able to do long haul travel from New Zealand in future? Currently I know Air New Zealand's looking at hydrogen, which will maybe get us to Australia. Problem is with hydrogen, it's hard to store in large quantities for long haul flights. So really we're looking at ways we can actually make sustainable aviation fuels. They typically have a carbon number with about 8 carbon atoms through to 16 carbon atoms, so reasonably small hydrocarbons. Recently we found out that we can come up with a way of using focused sunlight and a ruthenium cobalt single atom catalyst, so cobalt nanoparticles with ruthenium atoms embedded in it. We can actually produce these liquid fuels that we need that could be used as part of sustainable aviation fuels. So this is showing the value of metal single atom catalysts in supporting a renewable energy future. I'm quite excited about this work and where it's going next. So if I'm to talk about my career, Jeff, I know you love Janus, so I thought I'd mention it here. This shows my research productivity as a function of time. Obviously, I got out of a PhD in 2004, was on these fixed term contracts for a while, eventually got tenure at the age of 40 at 2012. This is my research productivity since, so this is number of publications per year versus citations on those. I'm really proud of where things have gone over time. This is atypical, I think, for someone who'd become professor at this university, where normally they'd have a fixed number of publications over an extended period. So I'm much happy to be at this part of my career than perhaps at the front end. And obviously in that first part I was dabbling between professional cricket or academia. The body's too old to even think about that now. But the skills I learned before I got tenure have really benefited me in the back end of my career and continue to do so. Obviously, plenty of people to thank. Students, I mean, I love teaching undergraduate students. One of the great passions and joys and responsibilities of being a university academic. The students love these mobile spaces where they can move desks around. They probably thought they'd get a better mark by putting it in the shape of a G. I was okay with it. And obviously a screenshot from some experiments we used to do in Chem 340 where we got this handheld XRF analyzer which enables us to go through and look at the chemical composition of different coins. So a lot of you might be surprised the $1 and $2 coin don't contain any gold. They look golden. But actually if you look at their composition, They're mostly copper with a little bit of nickel and manganese. Similarly, copper, you know, is that red colour there. If you look at a 10-cent piece, then it's mostly copper, as you'd expect. But if you look at the 50-cent piece, it contains a lot of copper. It's still 41% copper, yet it's colourless. It doesn't have the normal colour you'd associate with copper. So again, showing how alloying of metals together can introduce new functions. So my research at the university has been supported by a huge number of technicians over a long period, and often they get neglected when people are giving thanks for the contribution. So I mentioned them here. One of the good things about travelling and being internationally involved in research is I'm now published with over 1,100 co-authors. To me, this is a win. You know, the more scientists can get out and collaborate and publish with others, the more likely you are to do something useful. Obviously, plenty of supervisors and mentors along the way, top row. Then there's other people you just like to see around campus. Laurie Melton, Bob Anderson. Bob, I mentioned you earlier, that's why I haven't got your photo here. Bronwyn Smith, who's no longer with us, but my time in food science, she was a real good mentor. David Williams and Jeff Jamieson, I mean, critical junctions of my career. They've stepped up when there's nothing for them to get out of it, but have offered help and advice. And of course, occasionally, a bit of a live wire. You need people to rein you in, and Cather and Gordon have done that from time to time, and just say, maybe think about doing things in other ways. So it's important that I acknowledge them also. Obviously, family's a big part of anything, and one of the great joys of actually, living, I think, is having good family and having fun with them. So obviously my parents, Jane and Matthew, my dog Peppy, who was with me right through PhD studies. Yeah, but above all, my wife. Yeah, Dong Xiao. She just inspires and amazes me every day. Yeah, just like, yeah. I'm really blessed to have you in my life as my wife. So thank you, mate. Yeah. And thank you all for being here today. It's been special for me, and your presence has made it so. So thank you very much.